Okay. There, better. Because the only thing that's worse than hearing the sound of my voice is hearing it multiple times echoing through. Okay, so let's dig in where we left off. So we left off at isotopes, yes? So a couple of things that we want to sketch out and make sure. Okay, good, that's all set. Okay, so when we take a look at isotopes, we're looking at, and we kind of looked at this a little bit, like when we did this here, we kind of looked a little bit at carbon. So to kind of take a look at isotopes, basically what an isotope is an element that pretty much is the same. The only way they differ is in the number of neutrons that they've got, right? So the example we kind of looked at a little bit when we kind of did the little notational, the elemental notational sort of a thing, without really telling you about it, was we kind of looked at carbon, right? Carbon is kind of like the best thing to look at because we're mostly made of carbon and it's a stable element, and it forms an entire branch of chemistry, organic chemistry. And so what we want to do is we want to take a look at what an isotope is and use carbon as the example. And what we're going to do is we're going to give ourselves an idea of, okay, what does that mean for us? How do we use it biologically? Why do we care? And then what I want to do is I want to tie back into this idea here of half-life. Okay, so what we want to do, however, is we want to talk a little bit about isotopes, but we want to talk really specifically about this concept of radioactive isotopes and radiation, right? Because it's everywhere. You can't get away from it. So you're actually being exposed to it right now, which is a little freaky, but low levels of it, right? So it's not like we have, bomb grade plutonium in the basement or something like that, just sort of irradiating everybody in the building. It's not like that. Asbestos, maybe, but not plutonium. So let's take a look at it. So here we have carbon, right? But carbon basically is defined by what? What's your chemical ID? Oh, how much work we have yet to do. So what's your chemical identity? What defines you as what you are? How do we know this is carbon? Yes, right? The number of protons, your atomic number, right? So carbon has 6 protons, 6 and 6, right? So we learned that one before, the last time. However, you got 3 different flavors of carbon, right? So carbon 12 has 6 neutrons. How many electrons does carbon have? 6, always, right? Unless otherwise told, if it's naturally occurring, it's always assumed to be neutral. So the number of protons and number of electrons, because we're not talking about ions at this particular point, those aren't in play. Carbon 13 has 7 neutrons, right? And carbon 14 has 8 neutrons. So notice they're all carbon, but they're kind of slightly different in size because of the number of neutrons. Now, generally speaking, carbon 12 is the most abundant. So if you were to take a look at a carbon source just in nature, all the carbon atoms, and sort of define them a little bit, you're mostly going to find carbon 12. However, you will also find some carbon 13, which is less abundant, and carbon 14, which is the least abundant. Now, this is basically something that's true, like when you take a look at isotopes, throughout nature, right? So for instance, if I were to take a sample of carbon from nature, I don't just get carbon-12, I get all three of these in their relative proportions, right? Now the lion's share obviously is going to be carbon-12, but there's going to be a little bit of carbon-13 in there, a little bit of carbon-14. In you, the carbon atoms that make up the molecules that are in you right now have the same relative abundance that you see in nature. So the same ratios of carbon-12 to 13 to 14 that exist in nature also exist in you. Okay, so that's just the pool of carbon that we have to pull from. And so that's kind of also true for any other isotope. Now, one of the things that I want to sort of kind of point this out, and here's how we know about this, right? So here's like one of the ways that we figured this out is because if we take a look at carbon, right? And so let's say we're a chemistry class, and so we're like, well, I want to take 1 mole, and I'm not going to go into what a mole is. That takes a long time in chemistry to figure that one out. And half the time after the semester, you're still wrapping your head around the idea of a mole. But let's say you have a mole of carbon, and you want to know how much its mass is, right? So technically speaking, you can take a mole of carbon, which is actually a physical quantity. You can actually, it's big enough to actually hang on to. And you can put it on a scale, and you can write out its mass. What would that mass be for 1 mole of carbon, pure carbon, elemental carbon? The number of protons plus neutrons, which according to this should be what? Right? So the number of protons is 6. The number of neutrons is 6. So the mass should be 12. What's the actual mass of a mole of carbon when we weigh it out? You're like, should I know this? Yes, you should. What's the number right down there? Yeah, right. The mass, the actual mass is 12.011. Think about it. 6 plus 6 equals . But I thought we just said the mass was 12.011. But the electrons are, there's only 6 of them. And they're like negligibly small. You're talking about 0.011 of a gram. That would be one hell of a heavy electron, right? Does anybody see the problem there? When you went through math, does a whole number plus a whole number ever equal a non-whole number? Are you scratching your head yet? Here's the question. Where's the fraction coming from? Last time I checked, a whole number, 6, plus a whole number, 6, equals a whole number, 12. Where does the 0.011 come from? Can you have a smidge of a proton? No, no more than you can have 2.5 kids, right? Because then you're asking the question, okay, which kid did you cut in half? And every family has their ideas, right? Because there's always one of us in the family that's like, yeah, when it comes down to the half, I'm the one who's getting on the cutting table, right? Right, so that doesn't make any sense either, does it? Because you can't have a fraction of a whole. It doesn't work in biology for functional reasons, right? It doesn't work in chemistry either. You can't have a fraction of a proton. So the question is still there. Where does this fraction come from? Oh, maybe it's just a carbon thing. Oh, really? Well, let's go ahead. Let's take other things that we know of and let's weigh out a mole of these and see what we get. Well, let's take a look at them. Are there any whole numbers up there? A few of them, but the lion's share of them are mostly not. So not only did your question not get answered, but now it's getting bigger. Because now you're saying, wait. Apparently, in the chemistry world, it's not just an outlier sort of a thing, but apparently a whole number plus a whole number equals a non-whole number in chemistry. like by a lot. Now you talk to a mathematician and they'll look at you like, you need to go back to the drawing board because that's not universally possible, right? The universe is defined by mathematics, and mathematics is unyielding in a lot of ways. So the question is, where does it come from? Well, where does it come from? These guys. So when we actually put up the elemental data up there, we're looking typically and characterizing the element typically based on its most abundant version, which would be carbon 12. Okay. However, because these are less abundant, I mean, we're talking fractions of a percent in nature, but they're there. They're just enough because they're heavier, they've got more neutrons on them to skew the overall mass. It's kind of like when you're weighing out that 1 mole of carbon on the scale, it's like the heavier isotopes that are naturally abundant are kind of like putting their thumb on the scale a little bit. Now, the question is, you can tell actually how abundant these isotopes are, generally speaking, just by looking at them. How can you tell? Well, let's take a comparison. Let's take carbon, for instance, which we know is 12.011, right? And let's compare it to gold, which is 0.97. So the isotopes of gold are more abundant. Why? Because they've got a heavier thumb pressure on the scale. That's the reason why they're getting up to 1, right? They're like 0.8, 0.9. That means those isotopes, the heavier isotopes, are more frequent in nature. So you expect to see more of the heavier isotopes of gold than you would, say, for instance, of carbon, which is closer to 0, but it's there, which means there's not as much of the heavier isotopes in nature. If you take a look at something like oxygen, you're basically saying, well, there's really, I mean, it's 0.00, right? So you're basically saying, well, there's really no other isotopes of oxygen out there to do that. In nature, right? We can create them as much as we want in the lab, but we're just talking about naturally occurring isotopes. And so you can get an idea of how much other isotopes are by just looking at that fractional number. Okay. Now, what does this all mean? And how does this all apply to us? Well, first of all, let's kind of define what life is like for these guys. We said that carbon 12 is the most abundant. It is also the most stable. Carbon 13 is less stable. And carbon 14 is the least stable. So if you take a look at it, basically carbon 12 is happy, carbon 13, carbon 14, no. Okay. So the more unstable you are, then the more unhappy you are. And as an atom, if you're unstable, it's usually because you're getting too big in your nucleus. It's like the shopping idea, right? When your arms are loaded up and you're basically waddling around with your arms too full and you have to unload, that's what you're talking about. So when you offload some of that extra stuff to become more stable, then that's what's happening here. You have an unstable nucleus who's unhappy with who they are. And then you have to solve this problem, right? Remember, this is the one thing I said, that this is the one violation of atomic ID, the atomic number, right? I said, generally speaking, atoms don't want to change their identification. That's true. However, the one case where you will be willing to change your ID is if you are able to shift to an alternative identification that is more stable. And that's exactly what carbon 14 does. Carbon 14 is naturally radioactive, which means it is shedding particles or shedding mass or changing its identification to become more stable. Now, what it does is, if you take a look at carbon 14, generally speaking, we'd say, well, wait a minute, if I've got too many neutrons, what do I want to do? What would be my solution to the problem? You're too big. What are you going to throw out? You're going to throw a proton out? You prefer not to, right? It depends on how unhappy you are. But no, you would probably throw out what? A neutron, and that's basically what happens. So you're going to take a neutron in this particular case, and this neutron does something very weird, and that I don't know what the background particle physics is on it because I'm not a particle physicist, nor do I have any ambitions to be so at all, like zero. It's an interesting world, but that's there's just some mathematical calculations that I'm just not interested in venturing into. I can admire them museum style from afar, behind the velvet rope. I don't need to get in there and tinker with it. But I'm glad other people do, because it gives us answers. I'll wait for the nice answer, right? So this is what happens. So you get rid of this neutron. When you basically get rid of this, it's going to come with a release of energy, which is radioactivity. But here's the problem. Is it a good idea to just start spitting neutrons out there? Why not? There's no harm, no foul, right? I mean, they're not charged. If every radioactive element just basically shot neutrons out there like this, what would happen? Oh, you guys got to learn your nuclear physics, nuclear chemistry. You got to learn about nuclear bombs. Anybody recall a clever little toy that we invented back in the 40s called the neutron bomb? It's a version of the hydrogen. So they had the hydrogen bomb, and now you have the neutron bomb. The neutron bomb is a variation of nuclear technology. So instead of taking nuclear material and bringing it together to reach critical mass where it becomes unstable and then explodes, basically a nuclear explosion is a massive accelerated decay process where a mass of radioactive material is so unhappy and so unstable that it just basically irradiates and starts shedding material like quickly. I mean, it's so incredibly unhappy. Most isotopes that are stable will shed that radioactivity over time. So they're not just explosive, they just kind of shed it over time. But here's what the neutron bomb did. Basically what the neutron bomb essentially did was emit neutrons, which basically has the effect of like playing marbles with the universe. If you've ever played marbles with the universe or pool, pool's a good idea, right? What's the first thing you do in pool? Yeah, you break it, right? You rack it and then you break it. Well, the neutron is like the cue ball. The rest of the universe is like all the other balls that get scattered. Only in this case, imagine the balls never come to rest. They keep going around and pinging around and then ramming into other racked balls, which then explode and they start pinging around and start running into other racked balls. So a neutron bomb, one of my favorite examples of the chain reaction effect of nuclear bombs, including the neutron bomb, was a video a long time ago. It was like a video in the 80s where some poor soul, probably an undergraduate, basically set up mouse traps in a big room and set up hundreds of mouse traps. I mean, possibly even thousands. It was a pretty big room. And it was just like every inch of floor space was covered with a set mouse trap. I mean, the whole room was filled with it. And then what they did basically was they took a ping pong ball and they said, this would be a neutron. The mouse traps would be like the rest of the matter in the universe. What's going to happen as soon as that ping pong ball hits? The first mouse trap will get sprung, right? But then it will spring the others because it'll hit the others. And then the others will hit the others and the others will hit the others. And pretty soon the entire room just like chaos for a second and then quiet. And that's exactly what a neutron bomb does. The neutron goes in there, breaks up an atom, which then explodes, and then it'll break up other atoms, which then explodes, breaks up other atoms, and then eventually you've got a mushroom cloud and then the annihilation of matter. Oh, the games we play in the 40s when we're smart and stupid at the same time. Right, so that's basically what happens when you release a neutron. So is this a good idea? Yeah, not so much, right? So because we don't want to set off a natural neutron bomb effect and annihilates existence. Typically what happens with carbon-14 is it does something in physics that's weird, and I'm not quite sure what the physics is behind it, but it converts this nitrogen into a proton. And in this case, you hang on to it. So that's nice, right? So you didn't release a neutron out into the world, so you're not basically exploding and ripping the fabric of matter apart with your little neutron pinging all over the place. And what happened to carbon-14? What is it? So how many protons does it have now? Yeah, it's got 7. And who has 7 protons? And what is the mass of nitrogen? And what's the mass of carbon-14? Nope. Carbon-14. So that works out nicely, doesn't it? So carbon-14 is unstable as carbon-14. It takes one of its neutrons, converts it to a proton. It now changes its identity. It now becomes nitrogen. But as far as nitrogen is concerned, is it fairly normal? Yeah, right, because it now has how many protons? And nitrogen has, it now has how many neutrons? How many does nitrogen have? And how has a mass of what? It doesn't change, right? And the mass of nitrogen is. So it goes from being a relatively unstable, unhappy carbon to a relatively well-adjusted, pretty much run-of-the-mill, everyday nitrogen, which is the most abundant and the most stable isotope of nitrogen. So that's an improvement. That's exactly what it wanted to do. But,
does it matter that it doesn't have the same amount of electrons?
so, I mean, it could pick up electrons. I mean, yes, that kind of gets in some of the interesting offshoots of what's going on here, because you would imagine then at some point, does it become ionic, right? And it could, and it depends on how happy it is as an ion. It could also easily just pick up an extra electron or form a bond with somebody. That's probably like what it would do, is kind of cover that electron issue by forming a bond with somebody. Right. So that's basically radioactive decay at the carbon level. And that same process, by the way. Now there's different particles and there's different strategies of decay. Okay, and when you get into like nuclear physics or nuclear chemistry, you talk about the different types of decay, like alpha decay and beta decay, gamma, those sorts of things. There's different ways that you can shed mass to get yourself more stable. This is just the way that carbon-14 does it, and it works. And every time you do this, you emit radioactivity, right? So Mac, basically, as you're sitting here, you're emitting radiation. Your carbon-14 is constantly decaying. Now, how do we put this to work for us? Because that's a little creepy, right? Now that we're walking around with little nuclear reactors. So how do we put this to work for us, Megan?
Does that have to like actually like remove any neutron before it becomes a proton?
So that gets into the mechanism of this whole process of how this actually works, which I do not know. I went about as far as to like, oh yeah, it converts a neutron into a proton. I never ventured into the, okay, what's the mechanism? How do you actually do that? Because you start getting into particle physics and you start getting subprotonic and neutron and the characters of a neutron or a proton. How do you actually mechanistically manage to create charge, which goes along with the electron issue? So there's any number of questions in there when you talk about the mechanism that the particle physics people dove deep into. I'm just not a particle physics person. So because in biology, when you get into particle, you're going down this rabbit hole in particle physics, which is a fascinating world. It's very interesting, the stuff they come up with, but I prefer to read it later. And because in biology, it doesn't matter for us, right? To kind of build a biological organism, it doesn't, that particle physics story doesn't affect us at all. And we don't really use it. And usually particle physics, it comes with lots of calculations. And that's kind of your life. The big secret of physics, being a physicist, is that you really do more math than anything. I mean, in chemistry, you do experiments and you measure stuff. In biology, same thing. In physics, has anybody ever seen A Beautiful Mind? Russell Crowe. That's actually off a true story. But we've ever seen like the glass, where you see people writing on like the glass, or usually equations and stuff like that. That's like physics. That's what you do for a living. That's what physicists do, especially theoretical physicists or physicists where you can't get to things because you don't have access to a super collider. So you kind of have to just predict it with your math and say like, well, my math predicts that this is true. And if this actual particle does this, then we would expect this equation to predict it. And it either does or it doesn't. And if it does, then it's like your mathematical equation was correct and you're correct, even if you don't have the ability to measure it. That's the cool thing about physics, is you can get answers without doing anything. Because math is so powerful, it like predicts everything. To the point where if it happens, mathematically, it has to be explainable. Right. So there has to be a mathematical explanation for it. That's the thing I love about physics, that I like to see from afar, but I don't actually want to get into the mathematics of physics, because that's just, prefer not that rabbit trail. Okay. So let's put this to work, right? There's a couple of applications, right, of isotopes and radioactivity. For you pre-health people, nuclear imaging is one of the things this goes to work. Anybody have a nuclear stress test, like a cardiac stress test? It's kind of like a variation of the one where you're running on the treadmill and they've got the EKG set up on you and you're kind of running, and they're basically trying to figure out whether or not you're going to die on their watch or not. And they're measuring it. So they're looking at the parameters and the function of the heart at rest versus in exercise. Well, there's a nuclear version of that. Which is actually what most functional cardiologists prefer. And that's a little loaded, but because I do know some cardiologists who don't do that particular test, but are really good at another particular test. But basically what a nuclear cardiology test is essentially what they want to do. And what they're all doing is they're trying to figure out how well does your heart work. And ultimately how well your heart works depends on how much blood is getting to your heart. So the question is, do you have a blockage in a major coronary artery that's feeding your heart? If so, then that region of the heart that coronary artery feeds should be deficient in blood. And the question is, can we see that? Instead of trying to measure it indirectly by having you run on a treadmill, can we actually see that visually? And the answer is yes, because what they do is they inject a radioactive tracer, an isotope, into your bloodstream. So they set up an IV, they put a radioactive isotope in there that's very low level, right? So it's not like a huge emitter. It's about the equivalent of 2 chest x-rays. And then of course that goes throughout your blood. So your blood is now irradiated, and you can't, it's not like you're glowing in the dark, so you can't see anything. But the cameras can't, right? They're sensitive. They're designed to pick up that radioactive emission, and they're very, very sensitive. So to the camera, it looks like you're glowing. And so everywhere your blood is glows. Now, when you take a look at your heart, everywhere your blood is glows. If you see a dark spot, that suggests that there is a deficiency in blood delivery there. That area of your heart is going to start to die. And none of that, but they can actually map from the area of your heart, they can actually map which artery and which offshoot is the culprit. And so if they see something like that, it usually kind of looks like a little donut where they kind of cut a cross section to look at it. So they kind of look at the wall of the heart, and they can see if there's like a dark spot in the donut, they know exactly where that is. So there's a blockage in this branch of the left coronary. Guess what? We're going down the cath lab, and you're going to get a stent, because if I let you go home, you may not come back. Right. And it's very effective. It's very visual. It's a great test. But that's an example of using radioactive isotopes in medicine. In order to highlight your thyroid, you would use a radioactive isotope of iodine, because iodine only resides in the thyroid. That's the only place in your body that you use iodine, is in the thyroid. So you can use radioactive iodine to highlight the thyroid region if you're taking a look at that. Now, those are medical, but let's kind of expand that a little bit, right? So one of the things that we actually have in terms of functionality is something called carbon dating. Anybody heard of carbon dating? Right. So carbon dating basically is a way to use isotopes like a clock. And so if you are doing something in a very linear fashion, like if every second you're taking a step, then I can determine how far you've gone by how long you've been doing, right? So I can take a look at you and I can figure some things out by extrapolating backwards because you are basically very regimented in taking one step per second. Okay. The same thing is true for isotopic dating. Carbon dating is probably the most popular one, or the one we hear about the most. And this is how it works. All isotope dating has the same background. Generally speaking, you're taking a look at the natural ratios of a non-radioactive element versus a radioactive element. In this case, you're looking at the ratio of carbon-12 versus carbon-14. So we know the carbon-14 is constantly decaying. That is to say that it is disappearing because it's being converted into nitrogen. And so constantly your carbon-12, carbon-14 ratios are changing. However, as you sit here, remember your carbon-12, carbon-14 ratios look exactly like nature. Why? Because when your carbon-14 decays, you continue to replenish the source, right? So as long as you eat food, everything you've eaten is made out of carbon. When you eat that, the carbon in that food source represents the natural relative abundance of all the three isotopes of carbon. So if you've lost a little carbon-14, the second you eat it, that is anything that's made of carbon, you replenish that loss. And as long as you're alive, you continue to replenish that loss. This is the reason why our carbon in our body reflects what we see in nature. The two ratios should be the same. Now, the second you die, you stop replenishing the carbon. Over time, carbon-14 will decay and the ratios of 12 to 14 will change. So down the road, when we dig you up as an ice mummy, we can say, oh, well, when did this person live? Well, I don't know. Let's do a carbon dating on them, right? Because the ratios of carbon in nature are one thing, and they're constantly being maintained. And then the ratios of carbon-12 and carbon-14 in you is going to be different. Why? Because you haven't been replenishing them for however long you've been dead, and they've been slowly diminishing in carbon-14. And so what we can do is we can extrapolate back, because this is like a very calculable type of a process. It's not linear, but it's very regimented. So we can basically look back and say, well, it looks like according to the differences, it looks like he started decaying about 3,000 years ago. So that means that this person last took breath on this planet around 3,000-ish or so years ago. Okay. That's basically how carbon dating works. That's how any isotopic dating works. That brings us to this concept of half-life. So when you're taking a look at isotopes, and especially like dating, one of the things you need to be aware of is this concept of half-life. Now, the half-life is defined as the amount of time it takes for half the sample to decay. So if this is my sample amount, this is my time, then right about here, when I'm about 50% of my sample, that is what's called my T1 half, my half-life. Half of my sample has decayed. Now, for carbon, that is roughly about 5,700 years, which is one of the reasons why we use carbon a lot, especially like in archaeology and things like that, because it's robust within the period of human recorded history. Okay, and we can like compare these dates with other types of dates and with other artifacts that we have. Right, the idea is if you have multiple ice mummies that you think were living around the same time, then your carbon dates should match. And so you do a lot of this in archaeology where you use some of this stuff as well. But here's the problem. And this is one of the weak points, right? So this is one of those things where, you don't have just carbon, you can use a lot of things. So in this particular case, carbon, you're probably looking at maybe using carbon for mostly archaeological purposes. And that's because of its half-life. So you can't really say, for instance, if you wanted to say, well, how old is this rock? When was this rock first formed? Indeed it is. Thank you very much. Okay. We are back in action. Thank you, Apple, for not playing nicely with everybody in the sandbox, which you never do. Okay, so what we're going to be doing as we go forward is we're going to be kind of juggling both of these, right? The spatial description of where they are in space versus the diagrammatic, that is classifying them in terms of their temperament and their behavior. And we want to do that because that's what we want to go after. We want to go after chemical behavior, and the personalities of each of the electrons is what's going to drive that. Okay. And so the one thing that we want to hang on to then as we sort of get a little deeper into this idea is this guy right here. So this is a definitional piece that you actually need to make sure you hang on to really, really well. And that is to say that basically when you take a look at one of these neighborhoods, one of these orbitals, by definition, you can only have 2 electrons per orbital. So your orbital is full at that point if you only have 2 electrons. So there's only 2 electrons per orbital. That's just kind of the way it is. Now, what happens if you have more than 2 electrons, right? Most elements do. Well, what that means is you have to create more orbitals, right? Just like what happens if the population of Denver exceeds the housing capacity? Well, guess what? You have to build more houses, right? That's basically what you do. So the same thing is also true here. Now, what I want to do here is what we have here is we have our Bohr example here, and this is our spatial. This is actually what it is. This is our orbital idea here. So we're going to compare them side by side as we start to go forward. And what I want to do when we're taking a look at an atom and we're sort of sketching this out is I want to build a Bohr system from scratch and kind of show you how we're going to build it out. So what I'm going to do is I'm going to use sodium, and sodium has how many electrons? $11, right? By the way, you guys probably can't see it because it's like way over here. So it's like, but you guys can. So it has 11 electrons. So when we diagram out these electrons, the first thing we have to do is open up what's called an electron shell. Okay. So that's basically what we're going to do. Which represents in the Bohr model is basically one of the rings, the orbital rings that we have in it. Now, each shell will have a certain number of orbitals in it. Okay. And none of that, but the shell itself will represent an energy level. And typically speaking, so here they're like lettering, they letter label the shells. I don't do that because it gets confusing. I tend to number them. Okay. So for me, I use numbered shells. In chemistry, they use lettered shells. It never made any sense. Like in a quantitative science, why would you go verbal, right? Why do you use letters when numbers make more sense? I never did understand that one. But this is your first shell. Now within this shell, you have exactly one orbital. That orbital is this guy right here. Now, you'll see that this is a spherical orbital. And it's in the first energy level. Right, that first shell. This is the reason why we call it 1s. 1 for the first shell, s for its shape, spherical. Within this, how many electrons can you hold? By definition, you can only hold 2 per orbital. So you only have 1 orbital, so you put your 2 electrons in that little 1s orbital. Good. Are you done? It's full, but are you done with sodium?
No.
So what do you have left? Yeah, so what's your next move? You got to open up another shell, right? So now you have to create another shell. This is going to be n equals 2. Now from here on out, so here your max is 2 electrons. Your max is going to be 8 electrons per shell. And this is basically what it looks like in the second shell. So this is your n equals 2 shell. So let's take a look at this one. What orbitals do you have in the second shell? Well, you have 4 of them, actually. You have one spherical that, notice it's a little bit larger than the first shell, right? So that's a different shell. So they're not the same, but it is spherical. So you call it 2s. Okay. And then you have 3 what's called p orbitals. So they're in the second shell, so they're 2 p orbitals. That's what we call them. But the p orbitals are shaped like peanuts, and they basically will inhabit all 3 dimensions of your axis. So you'll have an x-axis p orbital, one along the y, and one along the z. These are each individual orbitals. So how many electrons can you put in this z orbital? 2. By definition, it's one orbital, you have 2 electrons. How many electrons can you put in the y orbital? 2. How many in the x orbital? How many in the s orbital? How many altogether in the second level? So your max is 8. Are you done now? So let's go and put our 8 electrons in there. 1, 2, 3, 4, 5, 6, 7, 8. Are you done? What do you have to do now? So you do what? Open up the 3rd shell. And what do? Add your little 1 in there, right? That's what you got left over. There it is. There's your Bohr diagram. But notice you have your Bohr diagram, so you're diagramming out the electrons according to shell, right? But that's not the way they actually exist in space. The way they actually exist in space, when you put all this stuff together, is they look like this. So you'll get all your s orbitals kind of all in there together. You get all your p orbitals in there together. And if you have more, like if you have more electrons to put in there, then you're going to start to get to the 4th ring, the 5th ring, the 6th ring, and you're going to have all these p orbitals like all over the place. They're all kind of crammed in there. And eventually what's going to happen is this little cloudy ball right there will start to just look like a big sphere, right? With like these little ruffles where you see kind of the tops of the p orbitals in there. And so the more p orbitals you put in there, the more spherical it becomes, which is kind of where we get our electron cloud. And so that's how it exists in space, but each of the electrons themselves are diagrammed out in personality type by the Bohr, right? So that's where you have the Bohr model as a diagram of the different types of electrons versus the actual spatial model, the orbital model, where it actually describes them in space. Make sense? So a couple of things I want to note at this particular point, because the question came up in one of my other 1111, which is a good question, by the way. And it also kind of describes a little bit about the reality of sort of driving this home a little bit. So number 1 was a student astutely recognized that the nucleus is positively charged. The electrons are negatively charged. So why don't the electrons just crash into the nucleus, right? Because positive attracts negative. So why don't the negative charges see that attractive positive charge and just go right and stick right to the nucleus? Well, the reason is because it is true that positive and negative attract. It's also true that negative and negative repel. So as they all come careening to the center of the nucleus, at some point they get close enough to the nucleus where they're getting also close enough to each other. And so, for instance, if we 3 were electrons and the nucleus are right here, we would all basically be attracted to the nucleus. But at some point, we would be getting like closer to each other because there's less and less space there. And as we felt each other's presence, we'd be like, wait a minute, I'm starting to feel more negative repulsion because you're also an electron than I am positive attraction. So what happens is you kind of put the brakes on. I can't get any closer because I'm already close to you. If I get any closer to the nucleus, then I'm going to get close to you too. That's like a double repulsion effect. So what happens is you kind of say, okay, wait a minute, this is more stronger to me now. So I'm going to kind of push away from you guys and we're going to create some safe space here. And that's as far as I go. Because I can't get any closer because I would have to get too close to my fellow negative charges. Okay. So that's one thing. The other thing is also in space, notice these electrons are all basically diagrammed out. But if you take a look at, say, for instance, a level 1 electron, which according to the Bohr model should never interact with a level 3, yes? Just like the Earth has nothing to do with Jupiter, we will never get anywhere close to each other. We will never cross each other's paths. That's not true here, right? Because what we have here is the spatial sort of thing. What we have here is just the diagrammatic personality. So it's possible that in three-dimensional space, like let's say that you're a level 4 electron and I'm a level 1. According to the Bohr model, we should never see each other, ever. Like you're far away, I'm not. But in reality, what we see in spatial, it's like there's times when we could be like right here, like right next to each other. I'm a level 1, vastly different type of electron than you, a level 4. But we're like right here next to each other in space. Okay. And then of course we whiz around and I can come over here and now I'm right next to a level 2 and a level 6. Right. And then I kind of whiz around. So you have all these different electrons that are mixed into each other. And that's kind of that spatial idea. So this gets us to our energy levels. I want to plumb this one a little bit because this is the one that's going to help us a little bit. So that kind of helps to fill in this whole piece here, where we have sort of the energy levels of kind of our orbitals. But what we want to do is we want to take a look at the electrons and the energy of position. And that's where I want to go here. So here is an atom with multiple shells that have been opened up. This is a Bohr version. Right, so here they're lettering it again. So this would be, I would call this one n equals 1, n equals 2, n equals 3, and n equals 4. When you take a look at these shells don't all have the same energy. So when you take a look at that innermost shell, this is going to be the lowest energy electrons in the atom, is down here in that first shell. As you go up to the highest, this is going to be the highest energy in n equals 4. So those outer rings have the highest energy to them. And then you're basically increasing as you sort of go up that scale. So when I say that I'm a level 1 and he's a level 4, energetically, our personalities are, I'm a low energy electron, but he's a very high energy electron. So his energetic personality is very different than what I am because of that. Now, does that mean that we never come in contact? No, that sense of, you know, where you are in the ring is an internal personality trait. We can be right next to each other, but our personalities can be still very distinct. Okay. And that's kind of what it's like. Now, the reason why we mention this and where we get some biological benefit from this, which is actually an important idea, is in the ability for electrons to absorb energy. So what I want to do is I want to take an electron here at a low energy state. Let's say it's at level 1. Okay. And then what I want to do is electrons, if you were to beam an energy source, like for instance, in this case, UV radiation, to an electron, electrons can absorb energy. And so when this electron absorbs this energy, what's going to happen is it's going to jump up to a higher energy state. So this is what's called an excited electron. It's your normal state plus whatever energy you absorbed. Okay, and so that kind of puts you into a higher energy state. So what that means is a level 1 electron, if it absorbs energy, can jump up to a higher level. Now here's the problem. You can't stay there forever, right? At some point, you got to do something with that energy because you always want to go back to your lowest state, right? Your most stable state. So the question is, on your way down to your most stable state, what's going to happen? Well, there's two things that you can do. The first one is you can just let this go right on back down to its stable state. And when it does that, it's going to release the excess energy that it absorbed, and it'll release that as a photon of light. If it does that, this is fluorescence. How many of you guys like playing with black lights during Halloween? Oh, it's a shame. Go out, buy a black light. You can get good ones on Amazon. Get some fluorescent paint, go nuts. Like instead of carving the pumpkin, paint the pumpkin and set it outside with a black light on it. Much, much more interesting. One of my favorites was some dude in our neighborhood actually had a skeleton, and he actually had like an old oil barrel. And he actually had some sort of a water pump hooked up through the skeleton. And the skeleton was leaning over the barrel, like vomiting fluorescent fluid. And it was really cool because he had a black light on it. So it was like this fluorescing. And I asked him, it's like, what do you, and all he used was like highlighter fluid. for the, so he didn't like use anything special. He just used highlighter fluid and you put a black light on it. And so you had this vomiting skeleton. That's awesome. You can do so much fun stuff with a black light. But the idea is, I mean, we've all seen it, right? We've seen like fluorescent stuff where it looks like it's glowing under the black light. And the question is that actual light? And the answer is yes. Why? Because what happens is the UV radiation from the black light hits the electrons of the fluorescent paint. Those electrons absorb the radiation, they absorb the energy, they jump up in their energy level. And then when they fall back down, they release the excess as a photon of light that you see, of the color that you see. And that's fluorescence. And that, you know, that is kind of fun, right? So now I give you some ideas for Halloween. So buy the black lights now, by the way, because you'll get them a lot cheaper than if you try to buy them in October. You're going to get rung up, like serious gouging if you try to buy them around Halloween. But that's all cool. But is that biologically useful? I mean, maybe, right? I mean, you might be an organism where it's like, well, maybe if I sort of glow, I'm going to scare my predators as a warning sign to say, listen, I can kill you if you eat me. So don't eat me. But you don't necessarily have to do that. I mean, you can do other ways to do that, right? So you can do other color variations like the monarch butterflies, like just by experience, I can tell you right now, your predators are going to know you're going to kill them. They're not going to need fluorescence to do that. So that's not necessary, but it is cool, right? Kind of goes to that bioluminescence section of biology. It is a thing, but it's not common. So what's the other thing? Well, think about this for a second. You just absorb like a sponge, a whole bunch of energy for no cost other than just existing. And now you've got all this energy bundled up in this excited electron. So you're a biological organism. So capture it. And use it for a biological purpose. Otherwise, you're just going to lose it, right? Capture it and put it to work for you. How many of you guys have a cell phone? Everybody. Dumb question. How many of you guys love your apps on your cell phone? For some of them, it's like a love-hate relationship, right? But they're pretty handy, right? If the world never had apps, would your cell phone be as an attractive tool for you as it is? No, the apps are kind of what makes it, right? But what do you need to drive your cell phone? Yeah, where do you get that from? Yeah, your battery. But your battery doesn't just come with it for free, does it? Where do you get the energy for your battery from? Yeah, the outlet in the wall, right? So here you have a source of energy, just like the electron absorbing this energy, and it's there. It's there for the taking. It's just flowing through the circuitry of the wall. So it's there. So we can just let it go and have nothing come of it, or we can capture it. How do we capture it? Plugging in our charger, right? So, and we capture it with something, our battery. So we have a device or a structure that allows us to capture that energy. And then what we do, we basically slowly take that energy that we've captured and we put it to work for us to drive our apps. Same thing is true in biology. If you've got this energy that's been absorbed in this electron, don't just let it go. Capture it. Capture it in what? A battery? Well, no, not really, but a molecule. Put it into a molecule, right? Once you secure it in a molecule, then you can sort of play around with it and figure out how to use it to drive biological work. This is the beginning, by the way, of one of the major big biological questions of life. What is the foundation of being able to answer the big biological questions of life? It's on the list. What's on the list? What? Yeah, the energy, right? Because none of the other stuff on that list you can do unless you've got energy to do it. Remember we said reproduction has a cost. Growth has a cost. Development has a cost. Homeostasis has a cost. Cell organization has a cost. So you always start with your energy foundation. Well, guess what? you just stumbled on an incredible piece to that puzzle. If you're able to pull off this capturing, then you've basically set a foundation stone that's going to benefit you when it comes to actually getting energy, securing energy, so that you can actually use it to power and answer all those big biological questions of life. So this is the beginnings of getting that energy plan together, which is the reason why we start with chemistry, is because we have to build that foundation, that energetic foundation that fuels everything else that we do. Now, this looks like a topical shift, but it's actually related, right? Because if we're talking about energy plans, then we got to actually talk to that about the chemistry of those energy plans. And the chemistry of those energy plans, the metabolic chemical reactions of those energy plans, comes to us in a specific type of chemical reaction called redox reactions, which stands for oxidation reduction, or reduction oxidation in this case. So basically what this is this is basically the major reaction type that drives most metabolism in cell respiration, which is basically how our energetics chapter. So all of our energetic stuff, like when we look at metabolism and how to acquire energetic molecules and then use those energetic molecules, generally speaking, what we're looking at is a redox reaction. Now, a redox reaction is very simple. It's simply a reaction where there's two individuals involved. There's a molecule A and a molecule B. What happens is molecule A will pass an electron on to molecule B. It's basically like a relay, right? You just pass on the baton. However, in this particular situation, when you have this passage, there's always going to be a situation where somebody loses and somebody gains. In the case where somebody loses, it's called oxidation. In the case where somebody gains, it's called reduction. And in order to remember which is which, remember this little memory trigger. Leo, the lion, goes grr. A loss of electrons is oxidation, Leo, and a gain of electrons is reduction, grr. So here's so we're gonna see how simple this is, at least at the beginning. I'm gonna start a chain, and this is kind of the way metabolism works. It's not just one redox reaction, it's typically a series of redox reactions occurring between that are in linked reactions. So we're all kind of a cooperative. So here's an example. Who's got the marker? Me, right? Now who's got it? So I have lost it, right? And he has gained it. So oxidation, reduction. Now if he passes it on, now he's going through oxidation and she is reduction, right? And if she passes it on, then she will have oxidation and then reduction will go to whoever gets it, right? So that's basically how oxidation and reduction works. It's usually between two individuals, you're just passing electrons forward. Somebody loses it, that's oxidation. Somebody gains it, that's reduction. Oh, that's all cute, right? If we're just passing markers around. But the question is, we're not just passing markers around, are we? We're passing on electrons. So think of an electron instead. I want to sort of take that same idea. I'm going to use us three. But think about this as instead, to sort of get an idea what this looks like from the way it works in metabolism, is think of this as sort of like a pot of gold, right? Kind of like leprechaun style, right? So think St. Patrick's Day, you got the little leprechaun pot and it's full of gold coins and things like that. So what we're going to do is I'm going to go ahead and instead of taking this pot of gold and just passing it on, I'm going to take a few of those coins. And so I'm going to take my cut. And then once I do that, I'm going to pass it on. Now he's going to take some coins and he's going to pass it on. And she's going to take some coins and she's going to pass it on. So we've each actually acquired some money, yes? Now let's imagine that we are Team Bentley. So with any one of us individually, we don't have enough money to buy a Bentley. But when we take our cut, it gives us enough financial resources to where when we work together as a team, we have a pooled sense of resource where we have enough to buy the Bentley. Right? So we do that. Of course, then we lose the money, right? And we're back to where we were. And we also lose the Bentley, right? Because generally speaking, like if there's metabolism, we're not buying the Bentley for ourselves, we're buying the Bentley for the overall institution. So the president apparently of the college gets a Bentley, thanks to us. And then what do? We go back to the salt mines and we grab another pot of gold and we do it all over again. And we keep the Bentley going, right? So we're like Team Bentley. And that's the way it's like in metabolism. Because the idea in this particular case, the pot of gold, the gold itself is the energy that we get from the electrons. So when we actually pass it on from one to the other, we're actually taking a little bit of energy so that we can set up circumstances to achieve a greater goal, which is an energetic molecule that allows us to be able to do whatever we want. Okay, that's the Bentley. The Bentley in this analogy is a molecule called ATP. Some of you may have run into that one before. That's basically like a rechargeable battery in the cell. You basically charge it up. You can do whatever you want energetically. It's your energy source, just like your cell phone battery. As long as you've got that functional battery and a source of energy, that's where we're coming in. We have that source of energy coming in because we're taking that cut and we're putting that together so that we can buy the Bentley. ATP is the Bentley. Then for us, the gold coins are the electrons. And so we're passing them on from one to the next. Now, what happens if we stop and we don't do it? Well, guess what? We don't get a Bentley. We don't get ATP, which means we're not going to be able to do cellular work. And that means we die. Right? So that's basically how metabolism uses redox reactions to sort of move everything forward and to sort of ultimately, and that's the story of those energetics chapters. And that's kind of the cellular respiration chapter. That's chapter 7. Okay, let's take a look at some of the elements, and specifically, we've already been introduced to elements and what they are, so we're okay with that one. But really, let's take a look at the elements and the focus on electrons. So remember, we said we're going to zero in electrons, but we're not even interested in all the electrons. We're only interested in the electrons that actually determine chemical behavior. Which ones are those? It's not the first shell. I'm thinking back to sodium, right? So we built out sodium. We had 3 different shells there, right? The first shell, no. The second shell, no. The only one that determines chemical behavior are what's called the valence electrons. These are the outermost shells. These are the electrons of the outermost energy level for the outermost shell. These drive single-handedly the chemical temperament of atoms. Now, when you take a look at the periodic table, most atoms don't have a valence shell, that outermost shell, that's full. There's only one group actually that is, and that's over there in group 8. So starting with helium, that has 2, right? So it filled out the first shell. Everybody else is full. If you pull out the second shell, you get neon. The third shell, you get argon. The fourth shell, and so forth: krypton, xenon, radon, and then Og, whatever Og is. That's a lab creation. That might be somewhere in CERN, Switzerland. But those are the only ones, right? Those are the only ones that have that full outer shell. The reason why that's important to understand that everybody else does not have a full outer shell is because the nature of how you fill that shell is going to determine what? Your chemical temperament and the way that you behave chemically. By the way, guess what? If you're trying to build molecules to build a biological organism, this right here all of a sudden has your attention, because this is what you've been going for, right? You said, okay, great. I've got all these different elements. They all behave differently. But what I really want to know is, how do they bond with each other, right? What motivates them to bond? And how can I manipulate that to create what I want, like DNA, for instance, right? So this is the answer to that. If you want to be able to manipulate how atoms bond with each other to build biological molecules, then you need to understand fundamentally valence electrons and how they determine the behavior of atoms. Now, link this idea of the partial filling of this outermost shell in most atoms except for the noble gases, which is group 8. And what you get is a linkage to the ultimate rule. This is one of those ones where this should be your new tattoo. Right, so you want to know this one, because this really does, in concert with valence electrons, is what drives why atoms do what they do. Basically, it's the octet rule, which essentially states that all atoms strive to achieve a full outer or valence shell by bonding with other atoms. And this just isn't some passive desire. This is something that is like all-consuming for an atom. Unless you're like, this is like, we're getting to like levels of almost like mental instability, right? If you've ever had something that you've wanted so badly, or that you strive for so badly that it just like, it consumes you. And every time you wake up, it's like, that's all you think about. It's like, okay, what am I going to do today to get what I want? Right? Most human beings don't have that level of ambition. Like a lot of us, honestly, it's like, am I perfect? No. Am I okay with that? Not really, but it is what it is, right? I can sort of live through the rest of the day. No, not if you're an atom. It is not okay to not be perfect. This is perfect, right? Filling up that outer shell is perfection. And you are driven, like psychopathically driven, to achieve that perfection. And you will not sleep at all, or eat, or do anything except for drive for perfection. So somebody who is that consumed, we usually will seek help for them, right? But that's the way atoms are. They do not rest until they achieve their octet rule, their perfection, right? This is like atomic nirvana, only without the Zen component of it, right? You don't just sort of be at peace with yourself. No. This is like hardcore nirvana. It's like either you're perfect or this is just, I'm going to tear the fabric of the universe apart because I need to be perfect, right? So this is extreme. This is what drives atoms. Not only that, but when you get to your periodic table, in this particular case, how close you are to perfection determines how desperate you are to be perfect. Think about it. How many valence electrons does sodium have? One, right? We diagrammed that one out, right? And so oftentimes what we'll do is, since the inner electrons don't matter, just the outer ones, oftentimes we'll do electron dot diagrams for that, which is essentially just a record of the valence electrons, because those are the ones that are driving the atomic bonding. So sodium is 1. How about chlorine? How many valence electrons does it have? It's got 17 altogether, right? So it's got 2 on level 1. It's got 8 on level 2. How many do we have left over? 7, right? So 1, 2, 3, 4, 5, 6, and 7. And you got that 1 left over. How many does carbon have? So look over there. So 6 altogether, right? So 2 on the inner ring, and then you open up another one and you have 4. So the electron dot diagram just basically records just the valence electrons. So I picked these 3, because I want to illustrate that sense of chemical desperation, which is kind of an anthropomorphized version in chemistry of saying it's reactivity. Okay, so chlorine, really close to perfect, yes? But oh, so close, but not quite there. Okay. Sodium, also close? Well, think about it for a second. How close? What does chlorine need to do to become perfect? So gain 1 and it'll be happy, right? How about sodium? How far away is it from being perfect? So it needs what? 7. Is there an alternative for sodium? Okay, if it does that, what happens? So if it loses that one electron, what would happen? Would sodium be okay with that one? Wait, what? Well, that's, you're ahead, a few steps ahead, but you're right. But could it achieve perfection if it lost one? Well, what's underneath that? Right? Because if you take a look at sodium, right? N equals 1 has 2 of them on there, right? N equals 2 has 8. N equals 3 has the 1. So if you lost that 1, what do you have left? Are you happy? It's full, right? So for sodium, you're like, wait a minute. I could either gain 7, that would fill me up, right? Or I could lose 1. Which one's easier? Right? For chlorine, it also has the same thing, right? It can gain 1, or it could lose 7. Which one's easier for chlorine? Yeah. So these are both pretty desperate, yes? They're really close. Think about it. I always like to think of this as like a race. And not just any race, right? This is like an Olympic race. Like you've been spending your entire life since you were little training for this, and like you're running, right? And so you're like right there, right? And so you get to this point in the race where you're literally like right there at the tape. I mean, you're like right there, and you're like, you can like smell the plastic, right? And it's like, you're just kind of like, well, I'm going to be like, right? If I just touch it, I win, right? Why? Because out of the corner of your eye, you see your arch nemesis who's right there nose to nose with you. At that point, are you pretty desperate? I mean, you're talking about an entire lifetime's worth of work right here, right here. This is the moment, right? You don't get this one, and you're basically never going to live this one down, right? You're probably going to be whooping on yourself. So what do? You cut your tongue out and you throw it over the finish line. Technically speaking, if it's still warm, it's still part of me. I win. Right? That's pretty desperate. But that person who's right there nose to nose, they're pretty desperate, aren't they? I mean, they would cut off their arm if they could and throw it across the finish line. So they're very, very desperate. Now, that's going to be different. So that's a different psychology, right? You're willing to do whatever it takes to get across that finish line first. Now let's take a look at somebody who's carbon. This is somebody who's like maybe 5 to 10 positions back in the race. Is carbon stressed out? No, because carbon's like, listen, I'm really not going to win this race. I'm not going to lose it either, by the way. But if I place in the top 5, I'm good. I'm good with that. Notice there's not as much desperation as that person who's running 5 to 10 back, because they're not that close to winning, right? And they know it. So they're thinking, you know what? If I place in the top 5 on the Olympic stage, I'm running against the best of the best of the best. That's no joke. I feel good about the fact that I'm even here, right? I mean, that's kind of it's a different psychology. They're not as desperate, but that also drives their temperament. Right? So when you take a look at atoms that are really, really close to being perfect, they tend to be very desperate to get over that last little bit, and they're willing to do whatever it takes. So if you take a look at chlorine, for instance, I always like to think of chlorine, just to anthropomorphize things, as sort of like hiding in sort of the proverbial atomic dark alley, behind the proverbial atomic dumpster, waiting for some poor unsuspecting atomic soul to walk by so he can jump on it, grab his electron, and be like, it's mine now. I don't really care if you're hemorrhaging on the street. This is mine now, right? So I don't really care. I've got mine, and I'm willing to do whatever it takes to get there. Well, sodium, on the other hand, is sort of like the same psychosis, only in the opposite direction. So with sodium, it's kind of like more like they're waiting for the unsuspecting passersby. You jump on them, you say, like, here, take my wallet. I don't want my money. Right? Of course, you're like looking around like, wait, I'm confused now, right? So was I just mugged? I'm not sure. You just gave me like $100 and you kind of beat me up a little bit. So I'm a little confused here. So, right? So it's weird. We don't have that actually in real life. It's like militant philanthropy, I guess. It's like, you know, you will let me do good to you. It's like, it's a little weird. Right, but that's kind of the way sodium is. Now, the thing is, the kind of cool thing about this is oftentimes hiding behind the same dumpster, you've got chlorine, and right next to them, you got sodium. And so that's like a match made in heaven. It's like, wait a minute, wait. So are you trying to tell me, chlorine, that you are desperate to get an electron? Is that what you're saying to me? It's like, yeah, that's what I want. I'm willing to do anything it takes. Really, because I'm willing to do anything it takes to get rid of mine. So why don't you take mine? You want it, I want to be rid of it, and we're both happy. So I've lost an electron, which basically means that I exist in my happy place as an ion, having lost an electron. Chlorine, also having gained an electron, is in its happy place and will exist as an ion. Notice we're both in our happy place now, aren't we? We've both achieved our atomic perfection, our octet rule, but we've only done so within the context of our relationship that we set up with each other. So bonds are basically relationships between two atoms to satisfy each other's octet rule. They are happy so long as that relationship exists. Of course, every atom would like to be left alone for eternity in their happy state, but are they left alone? No. Why? Because we had a slide last chapter called non-equilibrium. Just when it's all nice and happy and everything's good, like a bad soap opera, right? You have somebody cheat on somebody or do whatever. You tear apart the marriage that you just got done on Bold and the Beautiful, right? So you tear it all apart. You disequilibrize it. What does that mean for an atomic bond? You break the bond. So every time you break the bond to do something different and something new, you're throwing these atoms who were happy into a state of disrepair. And that screams for resolution. And that's good, right? So getting that resolution then will give you biological ability. And that usually turns out in our favor. So this is a good place to start. We're right about our witching hour. So we will talk about our naturally occurring elements at the beginning of the next time. Give me a couple of minutes. I got to get you guys quizzes together for lab. And so we'll be doing lab 3 and 4, mostly 4 is it. Like we didn't even do 3 yesterday with yesterday's section. So focus on 4. If we have time for 3, we will, but we almost never do. We really need to focus on lab 4. Make sense?